Is okay? Let's see. Look. Okay, so today we will, jump a little bit into result and techniques, and more or less the problem that I would like to analyze, in the next 2 hours are the following. So the first one is for a given model, or as general as possible. So given a class of constraint, so mu is always the product Bernoulli measure on the lattice, and we would like to know, for which value of the parameter p the measure is mixing, where mixing means the following, and maybe exponentially mixing, okay? So second problem is, so suppose that if the relaxation time is actually finite, okay, so the spectral gap is positive, then we would like to know how do they behave as a function of the parameter p. Actually, the relevant parameter is really q, so q is 1 minus p. Q is the density of the zeros, and the zeros are the facilitating sites, the one that allow flips, okay? And so a third sort of much harder problem is, so physicists would call it out of equilibrium evolution, which means the following, that you take as initial distribution for the process, not the stationary one, but some other distribution. For example, simple one, product measure, but with a p prime that is different from p. And question is, if you start from something that is different from the reversible measure mu, whether for a long time behavior you converge to mu, where f is a local function. For example, f could be just the value of the configuration in one point, say at the origin, okay? The simplest case. And of course, an even higher, and more difficult question is, if yes, okay, what's the pattern of this function, okay? And if I have time, we will describe that for one specific model, the ICE model. And so the last problem, that is an open problem, is the following. So I take the northeast model. So the northeast model, I remind you, is we are in 2 dimensions, and an update can occur only if the north and the east neighbors are at the same time 0, okay? And so imagine that you look at the northeast model in a triangle, and in order to ensure ergodicity, so it's just a continuous time Markov chain then, so in order to ensure ergodicity, you assume that all the vertices on this side and this side of the triangle are, say, 0, okay? This means that this vertex can flip, then the next one can also flip, etc. So certainly the chain is ergodic. So the question is, what is the mixing time of this chain as a function of n? Is it linear? Namely, is there like a front that is moving, starting from this corner and advancing, covering all the triangle in a linear time? This is it's reminiscent of last passage percolation, okay? And actually, the best bound that we know so far are n with logarithmic correction, okay? And really, to eliminate this logarithmic correction means that one has to really to understand something much deeper about the model. Okay, so so let me start with the first problem. And so in order to understand a kinetically constrained Markov process like the one that I described, it is absolutely fundamental to understand another process that is called bootstrap percolation. So Bootstrap Percolation is a monotone cellular automata, and it goes like that. So we are given a set of constraints, a collection of constraints. Imagine your favorite model, say, for example, the one neighbor model or the two neighbor model. So you need, in order to be updated, you need 2, 0. And so at time 0, so now time is discrete, it's time 0, 1, etc. And update for the automata are in parallel, namely at each time you update all the vertices of your graph, or your lattice in this case, according to the following rule. So at time 0, A is a random set, A on the lattice is a random set of zeros chosen according to, so the Bernoulli measure, according to mu. So to each vertex you assign 1 or 0 with probability P and Q, okay, and A is the set of zeros.
So are they independently done?
Sorry?
Are they independently done for all
Yeah, product. Okay?
Mu is a Bernoulli measure.
Yeah. It's a product Bernoulli measure, yeah. So A is the initial set of infected vertices. So in Bootstrap Percolation, you talk about infection, like in the lecture we had yesterday. And so 0 correspond to infection, okay? So at time 0, infection is concentrated on A. Then at time 1, okay, so the new set of infection, AT1, okay, is A union any other vertex X such that Cx of omega is 1. So any other vertex that was not infected and had, say, 2 neighbors 0, if we are considering the 2 neighbor model, then becomes 0, okay? You add to the infection, okay? And now you iterate, okay? So then you iterate, okay? Then for any time t a plus 1 is a t union all infectable vertices. At time t, yeah. Okay. So clearly the infection can only grow because you are adding, okay? You are never healing infection, so it's monotone, very, very different from the kinetically constrained model, KCM, okay? And so the main question in percolation is, okay, if I run this process for, infinitely long, okay, will I infect the whole lattice or not, okay? So you can define QC as the infimum of the value of Q such that probability that 0 becomes infected is 1, okay? And so for any given model, you would like to know whether QC is positive, maybe it's just 0, okay? And if positive, what it is, or bounds up on this number. So let me review quickly the model that we discussed, okay? So say the one neighbor model and its model. So QC is clearly 0, okay? Why is that? Well, for the one neighbor model, as soon as you have 1, 0 in your lattice, then you can infect all the neighbors, okay? You can continue like that and you infect the whole lattice, clear, okay? So for this model, as soon as you have 1, 0, you can infect all the vertices to, say, the right or to the left, according whether you are considering east or west, okay? And since we start from mu, we have infinitely many 0 on the line, and therefore we infect everything, okay? Easy, okay? Two neighbors. So two neighbors is a little bit more delicate, right? Because in order to infect something, you need two neighbors there, okay? So here QC is also 0, okay? Actually, at the beginning of the very early stage in the early 80s, I guess early 80s, Bootstrap Percolation, physicists did a lot of simulation and they concluded that for this model, QC was positive, and then the QC estimated by numerical simulation was lowering a little bit, while computers were improving, okay? And then finally, I guess, Fan-Enter proved that actually was 0. So maybe I'll give you now not the optimal proof, but a proof that is important for what I'm going to say on Saturday, okay? So why it is 0. Now, so why is not completely trivial is the following, that if you take Q, so the initial density of 0 of the set A, very, very, very low, okay? So you will have, 1, 0 here, then 1, 0 there, very rare a pair of 0 together because the probability is Q squared, okay? And then how do they move around? How do they spread infection, right? Okay, so there is some mechanism. The mechanism is the following. Sorry?
D doesn't play any role.
Here, no. No, for this model, no. Yeah. Okay, so imagine that Q is very, very small, okay? We want to prove that we infect the whole lattice. So consider blocks, so partition the lattice into blocks, okay? And you take the size of the blocks like that, C over Q log 1 over Q, with C, say, a constant that is large, okay? Now you can compute easily that if you take, so if you look at one block, then, and you look at the columns of this block and the rows of this block, with high probability, in each row and in each column, there will be a 0, because C is large. Okay, it's a trivial computation, okay? So then we call good, so a block is good if just the event that I said is verified, okay? So we just said that the probability of a block being good is high, okay? As high as we want by playing with this constant C, okay? So then, so by super easy percolation argument, if you look at the whole lattice, at the collection of this block, then the network, the good blocks will form a very dense network, connected, so an infinite cluster, so a connected dense network, with patches, finite patches of blocks not being good. Okay, so that's very, very standard. Okay, so imagine that then we have this network, okay, So each point here represents actually a block, okay, a good block, okay? And then somewhere on this network, just by ergodicity, there will be a block that, say, is completely filled, is completely zero, okay? It's very, very unlikely, it's completely, okay, but still there will be somewhere, right? Now, if, say, this block is completely zero, maybe I draw it like that, okay? This block is able to make this block here also completely zero, because here you will find a zero here, and therefore, say, for example, this guy here can also become infected because as a zero here, as a zero there, okay? So this column becomes infected, and then you continue, all right? So this completely zero block can propagate to the right, can propagate also to the left, and up and down, because we are also asking the condition on the rows, okay? Therefore, somewhere on this, so there is this super good block, very unlikely, but still is there, and this super good guy is able to infect the whole network, actually, right? Because he's able to travel along the network, okay, and infect everything. Therefore, we are able to infect the whole network, and then it's clear that we can infect all the finite patches because they will be surrounded by all zeros. Sorry?
You're defining an equivalent network in which its holding is coalesced into one particular zero node. Is that the idea?
No, I'm just saying that there is a very dense network of, say, here in 2 dimensions, okay? So there is a very dense network with only finite, regions that are encapsulated by the network, okay? And all the blocks in this network are good, and there will be at least one, actually there will be infinitely many, but at least one, okay? Block that is completely zero, okay? This block is able to infect all the other blocks of the network. Okay, and once you infect all the network, you can infect all the also these finite blobs that were not good. Okay, and that's it.
You can't identify a stable structure of one. It cannot be.
No. Yeah. Exactly. Okay. Okay, so okay, so there is so now I'll describe a general result. This is due to Ivailo Hortorski. In maybe like that, okay? Actually, result on, mixing of mu. So the first that obtained this result were Cristina Toninelli, Nicoletta Cancrini, Siri Roberto, and myself in 2008, okay, under slightly more restrictive condition. And Ivailo is a student of Toninelli in Paris. He sort of generalized that, but this is clean, so I will present that, okay? So he defines the following function, theta and q is the probability, is the probability that zero is infected for the bootstrap percolation in, say, minus n to the d, where bootstrap percolation in a box means that outside the box you don't put any infection. Okay, so you're just using whatever you can do in the box, and that's it. Okay, and he defines the following number q tilde c, which is in principle different from this one, which is the inf of q such that sum over n theta and q is finite. Okay, so in general, this is bigger or equal than QC by, that's almost obvious. But actually, they are conjectured to be equal. In all the model that we consider, they are just equal. And, okay, so, and then you can prove the following, that, so if Q is bigger than Q tilde C, then theta n decays exponentially. In n, okay? And that actually used this very recent approach based on randomized algorithm to prove sharpness of the phase transition for percolation by Duminil-Copen and Tassion. It's a beautiful, really beautiful proof. And so so if Q is less than Q tilde C, then the probability that the infection time for the bootstrap percolation of the origin, so this is how many iterations of the bootstrap map you have to do in order to infect the origin. So the probability that this is bigger than, say, n, say t, this is bigger or equal than a constant over t in n. Okay. So very slow decay as at least a lower bound. In particular, so the average of the infection time of the origin is infinite, right? Because it's the sum of this, which is infinite. All right. Good. Okay. So now we can finally formulate the theorem. The first theorem is, so if Q is bigger than Q tilde C, so mu is mixing, is exponentially mixing. Oh yeah, sorry. Not infected. Not infected. Yeah, sorry. Okay. Okay, so this is the main result. And since for many models Q tilde C really coincide with the bootstrap threshold, okay, this means that so in general we expect that as soon as we are above the bootstrap threshold, then the relaxation time is finite and the mu is exponentially mixing. Okay, so let me try to describe the main step of this theorem. Sorry? When you say exponential mixing? Oh, exponential mixing simply means that if you consider so the average of the over the process starting from mu of f ptg, so pt is the semigroup of the process, okay? This converges exponentially fast to the product of the mean. And what are the fg's from? Say local. So depends on finitely many variables, okay? But actually they should be just L2. Okay, yeah. Okay. So proof A. Okay, so if Q is bigger than Q tilde C, there exists two directions Okay, so I'll describe the proof only in 2 dimensions, okay, because I have to draw a picture. Okay, there exist two directions, A, B. Okay, let's say, and I will always draw A, B like, you know, the horizontal and vertical direction, just for simplicity. So I take this A and this B, okay, but they don't need to be orthogonal, okay? Such that the following happens, okay? So imagine that you take a box which is a parallelogram of side n along the AB, and you do the following construction, which is very reminiscent of the Northeast model. So call this box lambda naught, call this, let's say, lambda 1, lambda 2, and lambda 3. Okay. So there exists these 2 directions and an event, a good event, then G in in 0, 1 to say, well, one of these boxes, say lambda naught, okay? Such that mu of G is bigger than 1 minus epsilon. So for any epsilon is bigger than 1 minus epsilon, if n is bigger than a certain n p epsilon. So if n is large enough, so this good event is very, very likely, okay? And 2, and that's key property, if G occurs in lambda naught, no, lambda 1, sorry, lambda 2, lambda 3. Okay, so if all these 3 boxes are good, okay, this is reminiscent of the Northeast model, actually of the Northeast and Northeast model, because North, East, and Northeast, okay? In which we required, okay, originally in the model we would require 0, 0, 0. Now we require good, 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 okay? So then lambda naught can be infected without using any other infection. Outside, you know, lambda naught, union lambda 1, union lambda 2, union lambda 3, okay? Okay, so maybe before, you know, proceed, okay, so this is a result I'm not going to discuss, but I'm going to illustrate this in the example at least, okay? So say one neighbor model. For example, okay? So we want to define an event such that if this event occurs here, here, and here, then this box becomes infected, okay? Well, that's very simple, and we want this event to be very likely. So that's quite simple. We just need to require that there is a 0 somewhere, say here, okay? Some zeros, maybe some 0 here, some 0 there, okay? Because as soon as there is a 0 here, all this box can become 0, and you can propagate infection. Actually, they are not even necessary in this case, but who cares? Okay? Now we want this event very likely, so we have to take in this case, n should be, so n squared should be like 1 over q, if q is small. If q is small. Maybe also 1 over epsilon, if epsilon is the error that we need there. Okay, because then it's very likely to find the 0. Okay, so easy. Okay, so if that is clear, I would like to erase this and discuss, say, the northeast model, which sounds a little bit more complicated. Okay, so northeast model. Well, here already yesterday we argued that in this case Q must be larger than 1 minus the critical oriented percolation threshold, because otherwise we already understood that the relaxation time cannot be finite, so there is no chance to prove the theorem below that. And then here the good event is the following. So take a box and ask that all the oriented cluster for all the points over this boundary and this boundary, they are, so all the cluster, oriented cluster, shorter than, say, if this is n, say delta n. Well, delta is small. Okay. Duret says that actually if Q is bigger than that, then the probability that this is not true is exponentially small in n. Okay? And therefore, if n is large, the probability of this to occur is very, very high. Okay? So this is a basic result from oriented percolation. So now, let us suppose that actually this event is true here, is true there, and is true also there. We want to prove that then we can infect this box completely. It is in order to infect this box completely, it's enough to prove that we can infect this guy, this boundary completely, because then we can invade. Okay? And now, well, each cluster here is short, so we can, eat it up from the tips. Okay, so we can make all this piece here up to, say, distance delta n completely 0. Okay? The one that are too close to this boundary, no, because maybe their cluster ends here, and here I don't have any 0. Okay, so maybe, okay, so. And similarly here, okay, so this piece is fine, this piece is fine. Okay, and here the same. Okay, so up to this part is fine. However, this part is also fine because the clusters are short, and then since they are short, they must end on this boundary, but this boundary was 0 by using this guy here, and therefore they also can be infected. I can repeat the same analysis on the other side. So I can infect the whole corner, and then I can infect this guy here. Okay. Good. Sorry? I don't remember now, but so Ivailo Hortorski in his work, he has a new bound. So yeah, but there are just either rigorous bound or numerical simulation. I don't remember the correct number. All right, so okay, but in general, it's possible. So for any KCM in 2 dimensions, it's possible to prove that this is true. Okay. And now we should understand what to do with that. Okay? Okay, so now comes a completely different set of ideas, namely, a generalized Poincare inequality. Yep. Okay. Okay, so this was done by, in 2008 by, Siri, Roberto, Cristina Toninelli, Nicoletta Cancrini, and myself. But then more recently, in 2018, in a paper joined with myself and Cristina in Annals of Probability, where we proved this in much greater generality. And so the setting is the following. So S and mu hat is a finite probability space. For simplicity, it's not really necessary. Okay. G is some event, and the probability of G is large. Okay. Okay. And then, so consider this space omega, which is S to the ZD with mu that is, mu hat. So at each vertex of the lattice, we have a copy of this space. Okay. And finally, define the following constraint, C I hat. So the event G occurs at I plus E1, I plus E2, E2, I plus E1 plus E2, which is exactly what I said here. So north, so east, north, and northeast. Okay. Then the following holds that if you take, say, for any local function, if you take the variance with respect to mu of function, okay, then this is less than 4 sum over I on the lattice, okay, the average of Ci hat, this guy here, okay. So, Ci hat is the indicator of this event here. Okay, so Ci hat is either 1 or 0, is 1 if this is occurs, okay. And then you take the variance only with respect to the ith to the ith space, okay, of F, and you average the rest. So you see that. Okay, so we call this is a constrained Poincare inequality for a product measure. So without this one and putting here a 1, that would be a trivial inequality for product measure, okay? So we are able to insert this and pay a 4. So this if epsilon is small enough, if epsilon is small enough. I don't remember exactly the numerical value for epsilon, but some number, I don't know, maybe 1/10, I don't remember, something like that. Okay? All right, so this sum here looks very much like the Dirichlet form of a generalized KCM, namely a KCM that goes like that. At each I, there is a clock of rate 1, so when the clock rings, you erase what you see there, and you put a new configuration from S, sample from mu hat, okay? However, you do that only if this constraint is 1, just the same, okay? So we prove that using basically martingale method inspired by old work by Yao. Okay, and okay, so I'm not going to prove this. Okay, but I'm going to explain how to use this in order to conclude the proof. Okay, so yeah, well, originally, so just with, I mean, this is a sort of the baby version, okay? This is a baby version with this simple constraint. With Christina, we had a more sophisticated version that, for example, would allow us to prove the following, that if epsilon is, if 1 minus epsilon is bigger than the percolation threshold in ZD, then this constraint could be that from I starts a path of sides that are all good, an infinite path of sides. So the constraint is no longer finite range, could be, you know, infinite range. So very, very general situation. No. So later on, I'll explain why immediately you see that for this kind of system, log Sobolev, but also entropy constant cannot behave well. Okay, so this will be right after this theorem. Okay. Okay, so let us conclude the proof having, you know, these two input, these two ingredient. So. Okay, so the whole idea is the following. In order to prove that the relaxation time is finite, our goal is to prove that the variance of f is less or equal than some finite constant, sum over x on the lattice, the average of our original constraints, say one neighbor, two neighbor, whatever model you prefer, and then the local variance at x of f. So this is our goal. We have this inequality which is different, however, right? Okay, so the idea is, first of all, is the following. So take S, so the set S, you take a 0, 1 to, say, these blocks here, okay? And mu hat is the Bernoulli P product on S, okay? And G, so, and G is the event that we were discussing before. So G, good event. So with this setting, we are exactly, we can apply, you know, directly this theorem, okay? And we have this inequality. So the whole point is to prove now the following, that if we take a generic term like that, we should be able to estimate this term by a sum of terms that look like this one, okay? Because then we do the double sum, okay? And we recover, maybe with some huge constant c, we recover this expression, but we have proved that the relaxation time is finite. Okay? So let me explain why that follows from our construction. Okay, so let's see. So yeah, well, G was a good event, and we already discussed that this good event can be taken as likely as I want by taking this n large enough, okay, but finite, okay? So, okay, so now we want to estimate a generic term, so maybe one generic term, say the zero term by translation invariance. So we have to estimate the following, the average of the C0 naught, then the variance. So the variance over the block at 0 means the variance in the block lambda naught, okay, F, and this guy, and this is saying that lambda 1, lambda 2, and lambda 3, there is some configuration that is good in each one, okay? And then we have to average over everything, okay? Well, so remember that the key property of G was that if G is verified in these three boxes, we can reach the all zero configuration here, okay? But now, so the variance in lambda naught of F, which is, is some omega lambda naught, omega prime lambda naught of mu lambda naught omega lambda naught mu omega lambda naught prime, and F of omega lambda naught, and then outside there is the rest, minus F omega lambda naught prime, and outside there is the same rest square, right? So that's the variance, okay? Well, the idea is very simple now, okay? So since what is outside lambda naught must satisfy this condition, okay? Omega lambda naught is able to reach the all zero condition. So we can add and subtract here the term F of all zero in lambda naught, we can add and subtract this term here, okay, and just compute the difference, okay? However, I mean, the bootstrap percolation is able to go from this configuration to that configuration by a sequence of legal flips, because it's able to, in fact, respecting the constraint, and therefore there is a path that is a path in the Markov chain space that goes from this configuration to that. This path might be long, but still is finite because we are in finite volume, okay? And then if you do a little bit of, very standard, basic, sort of canonical path analysis, okay? You immediately, you get easily that this generic term mu C naught hat variance lambda naught F, you can bound by sum over y in maybe just the union of the four boxes, okay, of C hat y, the variance yf, with some finite constant in front, okay? Then you plug this into the original sum. You do this for every site I, okay? And you end up with this inequality here, okay? Now, in doing that, I have definitely not follow an optimal, strategy, because maybe in doing that, I mean, certainly it's not the best way to go from here to there, going to first to all zero and then back to this guy, okay? So really now, we only prove that the relaxation time is finite, okay? So, another question and level of difficulty is what is really the size of this relaxation time, okay? So this is what I'm going to discuss now. Sorry, I have to finish the theorem by proving that, that if Q is less than Q tilde, so proof that if Q is less than Q tilde, then the relaxation is infinite. Okay, so here there is a little lemma that is really very simple, that says the following. So let tau naught be the it in time for the KCM process that the origin is infected. Okay, so it's the infection time for the kinetically constrained model. And then it is known that if we start from mu, the probability from the reversible measure, the probability that this is bigger than t, this is less or equal than exponential minus t over the relaxation time. And then there is a q here. This is just general theory of Markov processes. Okay, connection between heating time and Dirichlet problem. Okay, so in particular, that immediately implies that the average of this heating time is less or equal than the relaxation time over q. Okay, easy. Now there is also a lower bound, and the lower bound is very natural. Well, the heating time for the KCM, for the kinetically constrained, cannot be much shorter than the infection time for Bootstrap. Because if the KCM is able to infect the origin, this means that certain updates of the KCM, which are the updates of the Bootstrap, are able to infect the origin. And therefore, if the Bootstrap takes a very long time to infect the origin, the same should do the KCM. And in fact, there is a lower bound that says that this average is bigger than some small constant delta prime, the same average for the Bootstrap infection time. Okay. But we already proved that if q is less than q tilde c, this average is infinite. Because the probability that this infection time is bigger than t decays not slower than constant over t. Okay? So if this is infinite, then we are done, right? Because this is also infinite, and then the relaxation is infinite. Okay, so that's it. Okay? So, since I'm really done, yep. So maybe I'll just attack the problem of computing relaxation or mixing time in finite region and show that immediately you get that this log Sobolev or modified log Sobolev cannot behave well. So for example, let us take the IS model. So IS model on 1n. Okay. Already yesterday we mentioned that in order to have ergodicity, we need that, say, okay, so we are looking actually from left to right, so we need that here there is a zero that is frozen forever, so this guy can always flip, and therefore the chain is ergodic. Well, imagine that you start from all ones. Okay, imagine that you start from all ones. In order to put a zero here, so for sure it takes a time proportional to n, right? Because first you have to infect this, okay? Then maybe in the next one, and we are forgetting the fact that we can also heal back, okay? But in any case, I mean, there is like a front that is proceeding from left to right, and this front cannot proceed more than a constant speed, and therefore the mixing time for sure, this is, so T mix certainly is constant n, and actually you can prove that is really constant n, even we prove with Ganguly that there is a cutoff phenomena, so it's very, very sharp, okay? So, however, for the IS model, we know, so QC or Q tilde C is zero, so the relaxation time is always finite, okay? So in particular, it does not depend on n, and therefore, if the log Sobolev or the modified log Sobolev were, bounded order 1, then the mixing time would be bounded by order log n. But now it is n, okay, so it cannot be true, okay? So immediately this little argument says that the modified or standard log Sobolev constant here must be of order n, okay? And for most of the KCM, there is a similar behavior exactly because of the presence of this super bad, although very unlikely configuration that in order to be unblocked, you need to start from one point and proceed, at most linearly in time to unblock all the configuration. Okay, so it's a situation in which really we are working on thin ice because all we have is this relaxation time, and we have to try to extract from this knowledge all possible information about the evolution. This will be topic of next hour, okay? Sorry for being late.